Hello guys, I'm going to start by talking about the electrostatic force. So I'm going to skip page 2 in your packet, which basically talks about this idea of charge and the conservation of charge and how do you charge something. So I'm going to leave that for class because it requires a lot of demonstrations. So you have to actually see it live kind of. So I'm going to skip that part. So we'll do that part in class. So I'm going to go with talking about the electrostatic force. And I'm going to go right to the formula. And this formula should be pretty familiar, or should look familiar to another formula we talked about in the past. So the electrostatic force follows this formula here. It's K, which is a constant, Q1, Q2. Now, the Q's here, they represent something that we call charge. And that's what I'm going to talk about in class tomorrow, or next time we meet, over the distance square. Now, what's this D here? That's the distance between those two charges. Okay, so basically it looks like this, Q1, Q2, okay? These two charges will either attract or repel each other, and we'll talk about that in a second. And the D is the distance that separates these two charges, right? Now, the unit for charge is the coulomb, okay? That's the unit. The force is in newtons, obviously, and the distance is in meters. Now, K has a value of 9 times 10 to the 9th power. And if you think about the units for that, it's newtons per, or newtons times meters square over coulomb square. Okay? So now, the fact that this is a very big number, actually, before I talk about that, so let's compare this formula to something that we already know. That looks like the force of gravity, which is big G, the product of the two masses, divided by the distance between the masses square. Now this G here was very, very small. That's why this force of gravity only made sense for large objects. Now this K is much, much bigger than the G, which makes the electrostatic force a greater force than the gravitational force. And we'll do some demonstrations in class to show that. Now, what are the similarities between these two formulas? Well, they both follow the inverse square law. In other words, if the distance between the charges doubles, this force will be cut by 4. Okay? If the distance is cut in half, the force will be 4 times as much. And this force here is directly proportional to the product of the charges. This force here is directly proportional to the product of the masses. But one important difference between the two is force of gravity is an attractive force. It only attracts. So if I drop this marker, okay, it's always gonna Earth is always gonna attract it. With the electrostatic force, it can either be attractive or repulsive, and these are the cases. And you learned this in middle school or probably earlier. If this charge here is positive and this charge here is positive, right? They're going to repel each other. You guys learned that like charges repel and unlike charges attract. So there will be a force on this charge caused by 2 on 1, I guess. Okay, and there will be a charge on this one called F of 1 on 2. And those two forces are equal in magnitude, but opposite in direction. That's Newton's third law. If one of them is, and now this also applies if they're both negative, right? So the forces will be going away. But what happens if one of them is negative and the other one is positive? Well, they should attract. And the force that each exerts on the other, the forces are equal in magnitude but opposite in direction according to Newton's third law. So this is F that 2 exerts on 1, and this is F that 1 exerts on 2. The force always generates on the object or the charge feeling the force, not the one that's exerting the force. So those are the differences and the similarities between these two forces. All right. that's why I'm not going to do the simple problems in your packet. I'm just going to go for problems where I have multiple charges interacting with each other. So the first example that I'm going to do, which is not in your packet, is I have a charge here of 3 microcoulombs, right? So which means it's 3 times 10 to the negative 6, right? And then I have another charge next to it that's negative 2 microcoulombs, right? And I have a charge of negative 5 microcoulombs, right? Okay, and I'm going to separate them. This distance here is 0.1. It's 10 centimeters. So we'll remember to change that to meters. And this distance here is 20 centimeters. Now, what I'm trying to do, I'm trying to figure out the force acting on the 0.3, the positive 3 microcoulomb. I really don't care what's happening to the other ones. Okay? So negative 2 and 3. So I think this negative 2 is opposite to positive 3. So the positive 3 is going to be attracted by the negative 2. So I'm going to call that F2. That's for the 2 here. The negative 5 is also going to attract the positive 3. So that's going to be, I'm going to call that F5. Okay? And all I have to do now is just find out the magnitudes of those forces. Don't find the, don't use the negatives. Just find the magnitudes. And the reason for that, because the negative, when you're dealing with the electrostatic forces, does not mean right or left. It just means whether you're attracting or repelling. So if you remember the formula, is K, Q1, Q2 over D squared. Okay, so Fe is positive, doesn't mean that it's pointing right or up. It just means that Q1 and Q2 have the same charge, which means this means that it's a repulsive force. Okay? If Fe is negative, it means these two charges are of opposite sign, and we know that opposite charges will attract. So this will be an attraction. Okay? So just be careful with that. So when we're dealing with these problems, we're only going to find the magnitudes and let the direction that's showing graphically decide whether it's positive or negative at the end. Okay. So I'm going to try to find the magnitude of F2. So that's going to be K times 3 10 to the negative 6 times 2 10 to the negative 6 over the distance that separates them squared, and it has to be in meters. So I did the math already, so that should be 5.4 newtons. You do the same thing for F5. That's the force that the negative 5 microcoulombs exerts on the 3 microcoulombs here, right? So K times 3 times 10 to the negative 6 times 5 10 to the negative 6 over separation distance squared, which is 0.3 squared. And that should give us 1.5 newtons. Okay? Now, since they are both going in the same direction, the net force, the combination of those forces, is the sum of those two. So it should be 5.4 and plus 1.5, which is what, 6.9 newtons, right? Now, if they were going in opposite directions, I can do whatever is to the right minus what's going to the left. If they were both going to the left, like if they were going the opposite compared to this, I will do 6.9, but I will throw a negative in there. But that's optional because you can think of left as positive, which is also correct. All right, the next example that I'm going to do is 3 charges, but they are not in a straight line. It's 3 charges that form some kind of a right triangle. So I'm going to put a positive 2 microcoulombs here, I'm going to put a -3 microcoulombs here, and then I'm going to come here and I'm going to put a -5 micro. Okay, and I'm going to try to figure out the force or the net force acting on the which one did I want to do? I'm going to try to find the net force acting on the 2 microcoulombs, right? So this is the object of concern. So it looks like the -3 is going to attract it. Okay, and these 3 charges make a right triangle. So I'm going to call this F3, and the -5 microcoulomb is also going to attract it. So I'm just going to try to do it nicely. So this is going to attract it also. Not drawn to scale by no means. Okay. So I think I can find the magnitude of each first. So F3 is going to be 9, 10 to the 9th. And I have to give you the distance here. So this separation, this distance is 0.1 meters. This is 0.2 meters. Okay, which makes this whole distance here radical 0.05. You can do the math there. You can do Pythagorean theorem and figure that out. Okay. Times 3 e to the -6 times 2 e to the -6 over 0.1 squared. And this should give us, I have it somewhere. That should give us 5.4 newtons. I think we did that earlier. Yeah. And F5, that's the force that the -5 microcoulombs exerts on the 2 microcoulombs, right? So that's going to be 9, 10 to the 9 times 2, 10 to the -6 times 5, 10 to the -6. See how I'm skipping the negatives on the charges? Just looking at for the magnitude. Yeah, and the distance between them square should be 0.05. In other words, it's radical 0.05 square, which is basically 0.05. So this is going to be 1.8 newtons. And they're both positive. So you do the magnitude always. Okay. So I got the information from there. Now, I can find the net force 2 ways. I can do the chart method, or I can do the law of cosines if you want. So let's try it with the chart. So here's your x component, here's your y component. So I'm going to put F3 here, put F5 here, and the net will be the combination of those two. Okay? So F3, it looks like it has no x component, and the y component is negative. So, and all of F3 is pointing down, so that's just going to be -5.4. Okay? The F5, it looks like it's going right and down, so the x is positive and the y is negative. All right, so let's figure out what these components are. So if I take this F5 and I break it here, so it's, in other words, it's down and over. Okay, so these are the components. This is the y component and this is the x component. You can see that the x component is F5 times the sine of this angle here, right? So I can call that theta if you like, right? So F5x is F5, which is basically 1.8 times the sine of this angle. What I don't need to figure out this angle to figure out the sine of that angle. I see that this small triangle and this large triangle are similar triangles. So the sine of this angle is basically just 0.2 over radical 0.05. I hope you can see that. And if you do the math there, you should get 1.61. Okay, for the x component. Now, we can do the same thing with the y component. The y component is right here, okay? I don't need to figure out what this angle is to figure out the y component. Okay, so the y component is just going to be F5, which is 1.8. This is the adjacent side with respect to this angle in this small triangle here. So to find this, you have to do a cosine of this angle. What the cosine of this angle is just 0.1 over radical 0.05, okay? Which is basically half of what we got earlier, 0.8. And it's negative because it's pointing down. So now I don't need this stuff anymore. Okay, so you didn't have to find the angle to get the components. So this component is going to be a positive 1.61, and this one is going to be negative 6.2. Now we just make our triangle for the net force, so it's going right. It's got an x component of positive 1.61. It's got a negative component, a y component of 6.2. This is your net. And you can find this angle here. Okay, so and then you would say F net equals, I got 6.41 newtons, right, at 75.44, so I guess we can say 75 degrees below below the x-axis, but I think below the positive x-axis, or the positive side of the x-axis. Okay. Now let's try this with law of cosines. So if you want to do a law of cosines, we have to redraw it so that we make a triangle out of this, right? So the way I did it is that I kept the F3 there, and I came to the tip of it, and I put the F5. Okay, so this is F5 is 1.8. This is 5.4. And I'll draw the net in a different color. And this is the net. So we have to eventually find out what this angle is and what the magnitude of that right segment is. Okay. Now this angle here was 63.43. Right? Okay. Which means this angle here is also 63.43. So this is 63.43. Here, I don't think you have a choice. You have to kind of like find out what that angle is, which leaves us with 116.57 inside that triangle. Okay, so you have to get the angle across from what you're looking for. Now, if you do law of cosines here, it should be F net square equals 1.8 square plus 5.4 square minus 2 product of 1.8 and 5.4 cosine of 116.57. So if you want to find the net force, you just take the radical of that stuff. And we should get 6.41, just like before. So I'll leave that up to you. You decide what you want to do. Okay. Now we have to figure out what this angle is. So how about if we figure out what this angle is, and then we subtract from 90, and we get our angle here. Let's call that theta. So I'm going to find that question mark angle. So I can do sine of that question mark over 1.8 equals sine of 116.57 over 6.41, because this is now 6.41. And this question mark should be 1455. Okay. Now, if you take that away from 90, because this is a 90 degree angle, this angle here becomes 75.45, about 75 degrees. Okay, and you will say that it's below the positive side of the x-axis. Okay. And I think I'm done with this, right? So the next part will be answering solving the problems that are in the packet. See you later.